Okay, so good morning to everyone. Now, in last class, we have discussed about the problems related to the LRU, that is the least recently used technique, cache replacement policy. Now, today, the another technique. Now, we have seen that there are three techniques, that LRU, MRU, and Fifo. These are the three cache replacement technologies we have, but in our syllabus we have least recently used and Fifo, first in first out. This replacement policies is in the syllabus, MRU is not in your syllabus. So already we have seen about the LRU. Now today we will see the Fifo technique. Now the problem will be given like this, that consider a four-way set associative. Consider a four-way set associative cache with total 16 cache blocks. Now, these are set that four-way set associative mapping. That means the k value, the k-way set associative, there is the k value is 4. The k value is 4. That means we will divide the cache into 4 set. If it is mentioned two-way set associative, that means we will divide our cache into 2 set. If it is mentioned 8-way set associative, that means we will divide our cache in 8 set. But here it is clearly mentioned 4-way set associative. That means k value is 4. That is, we will divide our cache of with 4 set. We will divide our cache in 4 set. And what is mentioned? Total of 16 cache blocks. Total of 16 cache blocks. That means we are saying that there are our length of our how many storage of this cache is what? How many storage? It is 16 cache blocks. So 16 cache blocks, 16 and divided by, it is mentioned 4-way set associative. So from here we will get what? 4. That means each set can contain at a time 4 blocks. Each set can contain at a time 4 blocks. This is how we can get that 16 is the our total is this cache is capable of storing 16 cache blocks, and our here in this problem it is mentioned that it is 4-way set associative. So that means 16 divided by 4, we will get that number of blocks a set can capable of storing at a particular moment. That is 4 blocks it can store at a time. At time a set can contain 4 blocks. So here that is why 4 sets are present. So we divided like set 0, set 1, set 2, set 3. 4 sets are present. Now here the main memory block requests are, now here the main memory is set. The main memory blocks are done. Now we know in the set k-way set associative how we will do, using the k mod n. Using this k mod n formula, we will do what? In which set the memory block will go, we will determine that. This is a thing mentioned in our, if you remember, it is mentioned in our k-way set associative, that k is what? The block number, and n is the number of set. And depend upon that, which memory block will go to which set, it determines that. It's this formula. So first what we have? 0. So 0 mod 4. Now n is what? Number of set. So how many set here? There is 4. So 0 mod n. N means 4 here. So 0 mod 4. That means 0. That is, we will get the result as 0. That means in set 0, 0 will go. So 0 will go where? 0 will go to the set 0 position. Then the next is what? 255. So here it will be what? 255 mod 4. 255 mod 4. Now if we divide 255 with 4, that means we will get the result as the remainder as a 3. So that means in the third set 3, this will go in the set 3, because we will find, if we divided 255 divided by 4, then 4 6 are 24 and there will be 14. So 14 means there will be 255. Okay, so it will be 24 and 1 5. 15 it will be thing, and 15, so if we divide it with 3, so 4 3s are 12, that means 3 will be remainder. So if 3 will be the remainder, that means it will go to the set 3, so 255 will go to the set 3 position. Then 1 will go where? 1 mod 4, so 1 mod 4, that means in set 1 will go. Then 4 mod 4, so 4 mod 4, that is it will be 0, so that means the fourth block will go to the set 0 position. Then next 3 mod 4, 3 mod 4 is what? It will be remainder will be 3, so the third block will go where? The third block will go in this position, in the set 3 position. Then next 8, so 8 mod 4, 8 mod 4 is what? 8 mod 4, that means it will be 0, the remainder will be 0. 8 will go here, 8 will go in this position. Then 133 mod 4, so 133 mod 4, where this will be go? 133 mod 4, so if we do, then we will get the remainder as a 1, so that means in the set 1 the 133 will go. Then next, what is 159? Next is 159, so 159 mod 4, so if we do that, if we do this, then what will be the remainder? The remainder will be 3, so 159 will go in this position, no problem. Then 216 mod 4, so if we do this, then we will get remainder as a 0, so that means 216 will go to the set 0. Then next 129, so 129 mod 4, we will get remainder as 1, so 129 will go to the set 1. Then 63 mod 4, so 63 mod 4 means what? 63 mod 4, it will go where? 63 mod 4, so the remainder will be 3, so 63 will go to the set 3 position. Then 8, now you see 8 is already present because we have already done 8 previously, that means 8 is already present in the cache. 8 is already present in the cache, and if any memory block is present in the cache, that means what we say? It is the cache hit occurred, that means the cache hit has been occurred. So this means we do not have to determine in which position this 8 will go, because 8 we have previously determined. In which position 8 will go, we have previously determined, because 8 come previously, so that's why 8 will be in this position. We do not have to determine in which position it is gone, we only write it, because already this 8 is present in our cache. Then 48, then 48 will be, so 48 mod n, what will be? 48 mod n, the remainder will be 0. But here, from here the problem has been started. Now if you look in this cache, already 48 mod 4, that means the remainder is 0, the remainder is 0, so that means in set 0 position only this 48 can go, other sets this 48 will not go, only in this particular position, only in the set 0 position the 48 will be go. But already you see 0 4 8 16, already 4 memory blocks are present in set 0, then where I will use the 48? Now the thing arises that we have to allocate this memory block in the cache, but this memory block has to be placed in set 0, but in this set 0 already the 4 memory blocks we have, then where we will accommodate this 48? Now to accommodate this 48, we have to replace from here any block, any one block we have to replace, then only we can accommodate the 48. Now here it says, Fifo technique says fast in fast out. Now among them 0 4 8 216, which block came first? We know 0 block came first. Now the name suggests first in first out, that means among them which block came first? 0 4 8 216, 0 came first, so that's why 0th block will be replaced and 48 will be inputted. So 48 we will accommodate here, and this 0 block will be replaced and it will go to the memory, main memory again. So that means from the cache memory we move the 0th block to the main memory again. Now if in future we have to require, then we will replace any of this block. Among them we will see that which block will came first, that block should be replaced and 0 will be transferred again. This is the thing. Now we accommodate the 48 because we replace the 0 block and 48 comes. So that means now we have 4 blocks in set 0 present, that is 4, 8, 216, then 48. These 4 memory blocks are present. Okay, so then 32 comes. So 32, where this 32 will be present, in which we will determine that 32 mod 4. So 32 mod 4, 32 mod 4 means what? Our reminder will be 0. Our reminder will be 0, 32 mod 4. So that means what? In 0th set 0 position, in set 0 position, this 32 should be placed in 32 should be placed in 0th position. Now where this, if you see this 32 came, now where this 32 will be placed in set 0 position, but already we have 4 blocks present in set 0, that is 4, 8, 216 and 48, but we have to accommodate the 32 here only in the set 0, but already the 4 blocks present. Now we will do what? We will use the FIFO technique. Among 4, 8, 216, 48, which block came first? The 4th block came first. Among them 4, 8, 216, 48, 4th block came first. So we have to replace this 4th block to accommodate the 32. So 32 will be accommodated here. So like this we will use the 32. Now we will accommodate this 32 here. Then next 73. Now 73 is what? 73 mod 4. So 73 mod 4 means what? Our reminder will be 1. So that means we will place 73 here. But you see, no other set we do not have such problem, because already 73 when it comes, 4 blocks are present. So that means we do not have to replace anything. If we have to place here but no position or no position available, then we have to replace the block. So we normally we will accommodate 73 because there is no such problem arises. Then 92. Now 92 also, if we perform with this formula, then what we will get? 92 mod 4. That means it will be again placed into the 0th position. In the set 0 position we have to place it. But in set 0, if we see 8, 216, 40, 32, these 4 are present. Now where this 92 will be accommodated? Now to accommodate this 92 in the set 0, we have to replace a block. Now among 8, 216, 48, 32, which block came first? 8 block came first. So 8 will be replaced and we will place 92 here. Then 155. So 155 mod 4. So 155 mod 4 will be what? 155 mod 4, the value will be, our value will be, reminder will be 3. So that means this 155 we have to place in the set 3. But set 3 already, if we see 255, 3, 159, 63, this total 4 blocks are present. So we cannot accommodate that. And if we have to accommodate this 155 in set 3, so 1 block should be replaced. Now among 255, 3, 159, 63, which block came first? 255 came first. So we have to replace that 255 to accommodate this 155. So we'll replace this 255 and accommodate 155. And then the last block, that is 2. So 2 mod 4, that will be, our reminder will be 2. That means this 2 will be, we will place it in the set 2. So like this, it will be the example or the program will be given. So you have to, first you have to see which type associative it is given. Now it is k-way set associative mapping, it is given. So we have divided into sets. Now, if there is mentioned that full way set associative, then there is no such problem arises. We will replace any block, any position, we will give that. And if it is mentioned that it will be the direct mapping, then what we have to do? We have to check with K mod 4 that which block should be available to which line. In that case, it will be replaced as a line. So you have to check that first, and which technique it is mentioned, you have to look over that and do the example like this. Okay, समझ में आया सबको?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
Okay, so this is the type, this is the problems like this problem it will be given. So I will say that each and every problem it is in the class, I will not able to discuss that, but like this the problem should be done. So I have shown 2 examples, and like this the problem will be there, you will practice it. So if you will practice, then it will be clear. Okay, so practice like this problem. This problems mainly given from here. So this type of problem you will see. So note down that which way first in the problem it will be mentioned which type associative, that means which type of mapping, this will be mentioned in the problem. Then 16 cache blocks it is mentioned. This is what sometimes it will mention that cache is capable of storing 16 words. Like this it can also be mentioned, but here in the problem it is given 16 cache blocks. That means our cache is capable of storing 16 cache blocks. Sometimes it can given that our cache is it will be 16 words, cache capable of storing 16 words. Sometimes it can be given the cache is capable of storing 16 bytes. It depends upon, but like this you will see that first which type of mapping it is given, then what is the our cache capable of storing, cache storing capacity, then memory blocks should be replaced like that. So you will divide the problem like this. Okay, so first see like this and then do the problem, then it will be clear to you. Okay, so this is the technique with the cache replacement policy. So I will recommend you to practice it, then it will be clear to you much more, or and you will, if you practice it, then you will do much over that. Okay, so this is about the problem of cache replacement policies. Now today we will see the topic about the instruction level parallelism. Now first, knowing that what is the instructions level parallelism, we will know that what is parallelism. Now in computer architecture, the parallelism means that parallelism happens when we have the multiprocessor. Now what is the multiprocessor? Basically the multiprocessor is used, the multiprocessor basically we used for our increase of computation. Now in today's system, in each and every system we can say that multiprocessor system. So multiple processor means more than one processor is present in our system. So why this more than one processor is present? Now let's say we have a large program came. Now let's say our program is very much large. Now as an example, let's say this program, this is the program we have, let's say, and this program has mainly total in this program we have 4 instruction present. In this program we have total 4 instructions. Now if we use a single processor system, let's say we have a single processor. Now if we process this program, and let's say we are saying that each instruction, we have 4 instruction present in this program, and executing each instruction, our processor requires 1 unit of time. Our processor requires 1 unit of time. And that is what, this is the first instruction we have. This is the second, this is the third, and this is the fourth. So in our program, we have 4 instruction, and executing this each instruction, the processor requires 4 unit of time. 1 unit of time, sorry, 1 unit of time. Let's say small example we are taking. So executing each instruction, we requires 1 unit of time. So that means if there is a single processor present, to execute this 4 instruction, how much time it will be required? Anyone? How much time it will be required? We know that
4 unit of time.
yes. So 4 unit of time it will be required to execute. But if we divide the processor, and let's say there is multiple processor present, now instead of this one processor, if we use 4 processor here, that is like this, there is a processor chip, and in this what we have already said that 4 processor are present in our system. So, and each instruction, let's say the first instruction will be executed by this processor, the second instructions will be executed by this processor, the third instruction will be executed this processor, and the fourth instructions will be executed by this processor. Now you see, we know that each instruction's execution, we require 1 unit of time. That means in 1 unit of time, we are capable of executing 4 instructions, because we have 4 processor present. We have 4 processor present, and each processor is doing what? Each processor is executing an instruction. So that means what? Within 1 unit of time, we are capable of executing this 4 instruction, because we have 4 processor present in our system. So that means you see, efficiently, and these instructions are executed parallelly, because when this first processor is executing the first instruction, in this meantime the second processor is executing the second instruction. In that meantime, the third processor is executing the third instruction, and in that meantime the fourth processor is executing fourth instruction. So that means parallelly they are executing the instruction. So that means this will be what? In the 1 unit of time, the whole program will be executed. But if that is in the single processor system, then it requires 4 unit of time. So for time consuming and capable of efficiently executing, we use the parallelism concept. So that's why we use the parallelism in computer architecture, that we as a user wants that efficiently and what in small of amount of time our instruction is executed. That means if it is in a single processor, then it requires a 4 amount of time. But you see, in 1 unit of time also, this total program we can able to execute efficiently. So which one will prefer? Obviously we will prefer that in 1 unit of time our whole program should be executed. So that's why the parallelism concept came. This is the parallelism. Now instruction level parallelism is what? We can say that instruction level parallelism is the measure of how many of the operations in the computer program can be performed simultaneously. So it is the measure that how many of the operations, it is the measure of how many of the operations in the computer program can be performed simultaneously. So why this is, already we have said that It is the time saving and making the processor efficient. Making the processor efficient. ILP is mainly measured that at a time in a computer, how many processing can be performed simultaneously. That means how many processing can be performed simultaneously. That is measured by this instructions level parallelism. So as an example, you see, let's say we have, this is the case one, that in this case there is a program present, and in this program s equal to a plus b, d equal to c plus k, and l equal to z plus y. These three instructions is present in this program, and we have 4 processors present in our system. So that means these instructions will be executed the first processor, the second instructions will be executed by the second processor, and the third instructions will be executed by the third processor. But you see this fourth processor, it doesn't, because we do not have much amount of instruction. So this fourth processor in that meantime will be ideal. That means it will not do any work. So that means in 1 unit of time, within 1 unit of time, these 3 instructions will be executed. So ILP is what? Instruction level parallelism. We already said that it is the measure. It is the measure that how many operations a processor can perform simultaneously. So what will be the ILP? How many operations our processor can perform simultaneously? So we have seen that three instruction. This 3 instruction has been done. So we say that here it will be 3 and divided by 1 because it is within 1 unit of time. So the ILP ratio will be what? ILP ratio will be 3. That means ILP ratio is equal to our total number of instruction executed by by how many of time. This is the measure. So 3 by 1, our value will be 3. So ILP is what? ILP is basically the measure. You see, it is the measure that how many operations in the computer program can be performed simultaneously. So in 1 unit of time, we see 3 instruction is executed. So that means the ILP ratio will be what? ILP ratio will be 3 by 1. So the value will be what? The value will be 3. So in this case, we get case 1 that ILP ratio, if this is what, and we have 4 processor present. So the ILP ratio will be what? The ILP ratio will be 3. Okay. Then for case 2, in case 2, you see we have instruction given s equal to a plus b, t equal to c plus d, and u equal to s plus t. So that means here also the 3 instruction given. So what will be the ILP ratio? You will say that ILP ratio is what? You normally will say that ILP ratio is what? Because there is 4 processor present and these 3 instruction are present here. So that means this first instruction will be executed by first processor, second instruction will be executed by the second processor, and the third instructions will be executed by the third processor. So that means the ILP ratio will be number of instruction, or what will be the number of instruction divided by 1 unit of time. So that means the ILP ratio, you will say that it will be 3. But it is not that case. What will be the ILP ratio? Because there is a problem arises, and this problem we call as the shear dependency problem. Now, why this problem arises? Now you see s equal to a plus b. So the first instructions will be executed by the first processor, no problem. T equal to c plus d. The second instructions will be executed by the second processor. There is no problem. But in case of third instruction, you see in the third instruction, what is mentioned? U equal to s plus t. Now, what S plus T? So that means these two final value S and T. After that, we will able to perform this addition. After we get this final value of S and T, that means when these two instructions will be executed, and after that, when we will get the final value, then only we capable of performing this third instruction, because we see S plus T, we have to perform here S plus T. That means the final value, after getting the final value of these two, we will able to execute this instruction U equal to S plus T. That means at first unit of time, the first and second instructions will be executed, but in that meantime we will not able to execute the third instruction, because we have to wait. Now how many time we have to wait? We have to wait till we get the final result of S and T. When we will get the final result of S and T, then only we will perform the third instructions execution. We will capable of performing the third instructions execution. Now mean what? In the first unit of time, these two instructions will be executed and we will get the result. So after that, in second unit of time, the third instruction will execute, because after the first unit of time's execution, we get the result. Then after getting the result in the next unit of time, now this is what the second unit of time, we will execute this third instruction. So what will be our ILP measure or ILP ratio now? The ILP ratio will be 3, because to complete total, how many time required to performing this complete execution of this program? 2 unit of time. So that's why the ILP ratio will be 3/2 here, not 3/1. Why it is not 3/1? In that case, the 3 instruction is executed at 1 unit of time. But here we have seen that first unit of time, we have performed the first 2 instruction and get the final result. Now, after getting the final result, that is why it is required for execution of the third instruction. So the third instructions will be executed in the second unit of time. So that's why the ILP ratio will be what? Total amount of instruction, that is the 3, and how many unit of time it is required, it will be 2 here. Sorry. Okay, it is clear, the ILP ratio?
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so always remember what is mentioned. First, see the instructions. In instruction, if it is like that, case 2, then it will be required amount of time. Not in 1 unit of time, all the instruction will be executed. It will require much more time. Sorry, if it is like that. But in the first case, we have seen that within a small amount of time, our instruction get executed. Okay. So this is what we have the ILP measure. Now we will start discussing about the details of our multiprocessor system. So basically, what is multiprocessor? Multiprocessor means it is a computer or a system with more than one CPU. That is what we have said, that the processor is what we divided the processor in a system. The more than one CPUs are present, or more than one processor is present. Why we use that? To perform our execution in very high speed, efficiently, we require that. And in nowadays, if we have large amount of data, we have to execute the large amount of data, then we use the multiprocessor system, because there will be more than one CPUs present. That in the multiprocessor system, one thing there is, that is there will be the more than one CPU or more than one processor, but not in that case the other resources will be more than one. That is the bus, then memory, it will be one. That share bus, main memory, peripherals, it will be single present. Only that what? Only will be more than one CPUs. And multiprocessor system will do what? It has more than one CPU or more than one processor, but it share bus, main memory and peripheral devices in order to simultaneously process the programs. That means our bus, main memory and peripherals will be single, not more than one. It will be same, that it will be like that, it will be single. Only what changes we have done for multiprocessor system, we have used more than one CPUs. Now why? That is for our execution of the large amount of data in small amount of time. That is why we have done only increase the processor, increase the number of processor. But other resources are like that, that other resources will be single present. Only processor number we have increased. Now, these systems, these multiprocessor systems are, we say, tightly coupled system. Now, why we say that it is tightly coupled? Because here in the multiprocessor system, number of processor and number of CPUs are much more than one CPUs present there, and they are belonging to the one system. Now the number of processor increased, so that means this all the processor will be are close communication. That means they are in a close contact, because number of processor increased. So if the number of processor increase, that means they will be in our close communication. They will be in the close communication here. So that's why, and all this processor belongs to one system. One system has this number of processor present. So that means what? This all system, all the processor we say are tightly coupled, because they are in close contact for communication, in close communication. So that's why we say it is the tightly coupled system. The multiprocessor system is the tightly coupled system. And when this multiprocessor is used, we have already said that multiprocessor is used when very high speed required to process a large volume of data. Because if we required our amount of data is large, and we require that in small amount of time we have to process that data, this large amount of data, then we use the multiprocessor system, because it will be very high speed. In very high speed, we will efficiently execute the